Hello, my name is Matthew Noyes,
I'm Joe Rice.
I'm Anthony Castillo.
and this is our Lab 1 video.
So in this section of the lab, we examined a Cherney-Turner monochromator, and we looked at the difference that rotation angle of the diffraction grating inside the system has on the output image and its power. So here we have the setup. You can see there are two concave mirrors in the system and a lens going from the first mirror down to the grating, which is in the back left corner, and then to the far right mirror. And then that brings us through slits, and we varied the slit width. We had a 250 micron slit width and a 500 micron slit width. So here we have our data for both slits. You can see that for the 250 micrometer slit, we had a max power of about 1.2 microwatts, whereas for the 500 micrometer slit, we had a max power of about 1 microwatt. And you would not expect this. It's most likely due to some error, as the setup was pretty rough. But both these graphs illustrate the distribution we saw over these angles. This section of the lab illustrates two things. It illustrates the difference in diffraction orders of a grating, as we illustrated by looking at the M-1 diffraction order, as well as how to resolve the resolution bandwidth of a monochromator.
In this part of the lab, we used a helium neon tunable laser and a prism monochromator to study how different wavelengths diffract through the system. By tuning the laser and rotating the drum on the prism monochromator, we were able to find a relationship between the angle of the mirror in the micrometer and the wavelength of light that passes through it. The important principle that this monochromator works under is the principle of dispersion, and that different wavelengths of light will refract at different angles. Here we can see the relationship between the wavelength of light passing through the system and the angle at which the mirror has to be at in order to allow it to pass through. Dispersion is a very valuable technique in micrometers because it has a higher throughput than do gratings.
Again, we use the tunable laser to determine at which angle the grating on the Gerald-Ash monochromator needed to be placed to determine the different wavelengths. Here we can see the plot of the wavelength versus angle reading, and curiously, the gratings seem to be much more sensitive than the prism. In the next part of this lab, the slit function of the Gerald-Ash and ocean optic spectrometers were to be found. The slit function is an important aspect because to interpret the observed spectrum, the bandwidth of the spectrometer has to be known. This is because the finite resolution of these devices smears the original input spectra. Here, the slit function of the wavelength versus power for the Gerald-Ash monochromator is shown. Next, the resolution of the ocean optics spectrometer was found. Thus, its slit function was determined by using the Gerald-Ash monochromator and was found to be about 0.5 nanometer. Next, we looked at a continuous spectral source and line source, both with and without a spectral filter, in order to understand how photopic response affects discrimination of wavelengths. From these charts, we can see that both sources were emitting light, but wavelengths beyond the visible spectrum. We knew that this was true because when we added the filter, those wavelengths disappeared from the chart.